Alright, hello everyone. I'm trying to download a LaTeX editor, so there might be a weird pause in this episode sometime. But today we are looking at... I'm not as set up as I thought I was for this episode. I need to move my mic closer to my face. Today we're looking at the third Lie theorem. Of course, now it takes time to refresh. It'll take 10 minutes. So, the third Lie theorem. Theorem of Lie is what they call it. Let's keep our notation consistent, I guess. Man. And of course, throughout our base field is going to be real or complex. So we come to our first theorem, start things off, not the theorem in question. So this one says let G be a connected also can be simply connected. I don't know why they were connected and then simply connected. Lie group ignore that weird comma now. They kind of misled me. Of course, over our base field, we're going to let G prime be a Lie group over K. Not necessarily connected in any sort of special context. Of course, we're going to have lowercase be the respective algebras. Then there is our map from the homomorphism as Lie groups of G to G prime to sending to homomorphisms as A or Lie algebras from G to G prime is bijective. So essentially there is a one-to-one direct correspondence between Lie group homomorphisms and Lie algebra homomorphisms. So we're going to let T from an first algebra to the second algebra be a Lie algebra homomorphism. We want that there exists a unique Lie group homomorphism such that T is just the algebra version of phi. So, we know T extends uniquely to a local homomorphism F from G to G prime, which should be phi as well, of course. This is an apostrophe and a period, not an exclamation mark. Then the graph gamma phi and G. Okay, I said phi and I wrote a T, but it's an F. This of course going to be in the product of the domain and the codomain is an analytic subgroup chunk. We'll call h comma I the Lie group generated by is the generated Lie group. So we have a map then from H to through our I. It's going to be sending it to some point in G times G prime, which we can then just project onto its first factor of G, and this is equivalent to arp-C. Then C is a local isomorphism and as H is connected and G simply connected, C is an isomorphism onto an open subgroup of G. Since G is connected, C is surjective. We're going to let C be our second projection of I of C inverse. So you can kind of see how that would work. It'd be a map from G to G prime from our above chart. And this is going to agree with F in a neighborhood of E, so we know that our equivalent on the group exists. Now we need to show that it's unique. And unique, which is of course just by having phi1 and phi2 homomorphisms whose derivative at E is T must locally agree with F. So the set of points on which they agree must be both open and closed. So is just G. We have another theorem which the work is to prove a split up between the previous theorem here and our next theorem. This is that the category of both simply connected and connected Lie groups over either the reals or the complexes is equivalent to the category of finite dimensional Lie algebras. Now as I said, we already have our bijection of the maps. So we need the rest of what we need is given in the third theorem, which is the titular third theorem of Lie, which states that for any finite dimensional Lie algebra G, there exists a both connected and simply connected Lie group G such that the associated algebra of G is our given algebra. And we've already seen this before in different contexts. So this was first proven by Cartan, which we will sketch, after giving a shorter proof based on Ato's theorem. Alright, and here we can note it suffices to find a Lie group G such that all G is G, since taking the connected component H of the identity in G and then taking the simply covering group of H, we are done. So we don't actually need to prove that G is connected or simply connected or any of that, because we can just force it afterwards without interrupting our theorem. And so our first proof is based on another theorem, which is by Ato, which I believe we've already seen, but we will go over again, which is every finite dimensional Lie algebra has a faithful, that is injective, I believe, or is it surjective? No, it has to be injective. Injective, I don't know why my brain broke there for a minute. A faithful finite dimensional representation. And we've already seen that, so I don't need to prove it. So now we're going to let H be the Campbell-Hausdorff group chunk of G, and let T from G to the endomorphisms of some of V. My trackpad is breaking my thing here, tablet, making it harder. And we want T from G to the endomorphism of V be a faithful representation. Then T induces a local homomorphism F from H to the general linear algebra of V. Since T is faithful, F is an immersion at E. That is H corresponds to a subgroup chunk of the general linear Lie algebra group of V. So H is equivalent to an analytic group. Okay. And now we look at an alternative proof. My first part is when G is either semi-simple or abelian. Well, if it's semi-simple, the adjoint from G to the anamorphisms of G is injective. So we're done by the above proof. Because we don't need Ito's theorem in that case. Or alternatively, we can note that the image of the adjoint representation is just the derivations of G. So G is just the algebra of the automorphism group of G. Secondly, if it is abelian, we can take G as the additive group of G, and we're done with just that. Now we move on to the general case. And here we go by induction on the dimension of G. Now if G is in case 1 and the above, we are done. Otherwise, G is a semidirect product of it's an ideal G1 and a subalgebra G2, where of course each of these are going to have a smaller dimension than G. And we need a map phi from G2 to the space of derivations of G1. Now by our inductive hypothesis, by induction we're going to let each gi be connected, be simply connected, both connected and simply connected, Lie group, such that the ith algebra is the algebra of the ith group, and we will show that G is the algebra of G, where G is a similar semi-direct product of G1 and G2. And then, so we show, first off, that the derivations of G1 is the algebra of A1, with A1 being the automorphism group of G1. And secondly, we'll show that A1 is also the automorphism group of the first group. And thirdly, that A1 acts analytically on G1. Alright, so these are our 3 steps. First off, given an automorphism of G1A and an element of our group G hat, we want a neighborhood N of A in A1 and U of G in G1 such that the action of N sending an element of U to an element of G is analytic. We're going to let W1 be in G1. I'm going to mess that more, watch. This is going to be a neighborhood of 0 and G on which the Campbell-Hausdorff formula converges. We want to choose neighborhoods N of A in A1 and W2 of 0 in W1 so that the action of any element in N, which is of course in the automorphism group of G1, on W2 takes values in W1. Going to let V be the exponential of W2 so that the action of n being an automorphism of G1 on V is induced by the action of n in the automorphisms of G1 on W2. Since the elements of the automorphism group of G1 act linearly on the Campbell-Hausdorff formula, the action of n on W2 is analytic. So the action of n on V is likewise. Now, we need a new page. Since G1 is connected, there exists an integer, a positive integer n, such that G hat is in V to the n, being the set of products of n elements of V, which we can assume to be open. Actually, we're going to assume V is open such that V to the n, being the union of translates of V, is likewise open. And we're going to immediately switch out this notation Vn for U. We're then going to let theta be the action of A1 on G1 and immediately switch out that notation where theta of B on G on H is just BH. And we want to show that theta is analytic on n times U. Let the notation here is switching weirdly, and it's kind of weird. We'll let V to the bracket n be the n-fold product of V, and let C from, let's move from V of n to U be multiplication. And we're going to let theta underscore from n on our respective V to the n to the G by theta underscore of B, or element B from n on G1 through Gn be the product of Bg1 through Bgn. So that we have another diagram which we want to commute from n times v to the n. This theta underscore action is going to take it to g, as we saw. We can also apply mu to the right hand side, which is our multiplication, to give us an element of n times u, and this will actually end up just agreeing with our theta. And since theta underscore is analytic, to show that theta is analytic, we need this function mu from Vn to u to be a surjective submersion. Now, since G2 is connected both simply and not simply, C and this is of course true. Finally, to show, we need to show, since G2 is both kind of simply connected, V induces a function C from G2 to A1. So we define a semidirect product structure on G1 times G2 by the conjugate of an element of G in G1 by an element of H in G2 to be C of H times G and 0, which is of course analytic by the analyticness of, where's my mouse, C, and the action of A1 on G1. So that L of G1, I think that's the right direction, of G2 is G. And we are done. And we actually have another theorem which has a much shorter proof and then a bit of a remark, and then we'll be done this video. So that's cool. We're going to let G be a both connected and simply connected Lie group. Let G be its algebra and H an ideal of G. Then, first off, there is a closed, connected Lie subgroup H of G corresponding to our ideal H, and set H is also not only going to be connected but simply connected. So let's look at our proof for part 1. we're going to let K be a Lie group such that its associated algebra is G over H. Then the projection of G onto G over H induces an analytic homomorphism phi from G to K, since G is connected and simply connected. So then we take H to be the connected component of E in the kernel of E. That gives us H, our desired H. And secondly, since G over H is a Lie group, the second projection of G over H is 0. And then in the homotopy exact sequence, we have I need a new page for this. We can go into pi 2 of G over H to pi 1 of H to pi 1 of G. And we know that this one is equal to 0, and so is this one. So from that, pi 1 of H likewise has to be 0, since this is an exact sequence. And our remark is it seems likely that no simple proof of least third theorem exists, because it would need to extend to Banach analytic groups, unless it made essentially use of local compactness of R and C. So, remark: in a general Banach space, third theorem of Lie does not hold. For example, some of our earlier theorems actually don't even hold in general Banach space. We can take G to be the product of the general linear Lie group of H with itself, with H an infinite dimensional Banach space. Noting that we already know that GL of H is connected both regularly and simply connected. Then the center of G contains, sorry, one second. Oh, never mind, I'm losing my mind. So it contains the multiplicative group of the complex numbers times itself, which itself contains the simple circle times itself, which we're going to define to be z. Then the Lie algebra z underscore of z is contained in the center of the Lie algebra of G and hence any one-dimensional subspace H of Z underline is an ideal in GL of G. So now we're going to take, one sec, now we can take H to be the Lie algebra corresponding to the pairs mu v, where v is, well, let me write some new line. Our pair mu nu, where nu is an irrational multiple of mu. This is of course a subset of S1 times S1 with alpha being irrational. This subgroup is both connected both simply and normally connected, and is not closed in G. So we can't have this third theorem in a more general context. And that's our video for the day, for right now. Up next we're having Cartan's theorems. And then that'll be it. I'm going to be doing a homework. I don't know what anyone following along, theoretically, not actually, will be doing, but yeah. Maybe I'll come back to this later on. But for now, thank you for watching.